Okay, so we're going through the summer exams 2023. Question 1 was clustering. Let me paste it in. Okay, question 1, clustering. Oh, I don't know why the quality is so horrible. Okay, take that screenshot again. Okay, that's better. Clustering. Suppose we have 5 observations for which we compute the following dissimilarity matrix. Hello, James. Based on the given dissimilarity matrix, hierarchically cluster the observations using complete linkage. Sketch the dendrogram, clearly illustrating the height at which each cluster fusion occurs. Does anyone want to share their answer to this, or shall I just paste mine in? Or just talk me through how we do this. Yep, I am recording, Ash. Thanks for reminding me. Okay, let me paste in my solution. You can look at the highest CA... Yeah, so you can look at the highest CA linkage and cluster updating a distance. C# link it. Okay, let me paste my solution in and then. So I did this. I started with all of the points and looked at what distance they were from each other. So I just started with that original dissimilarity matrix, and then I looked at the smallest value. So x3 and x2 have the least dissimilarity. So I merged x2 and x3 at a height of 0.1. Yeah, they're all individual, so we just pick the lowest one right now. Yeah. So I merged x2 and x3 at 0.1, and then I merged. So after drawing out the next dissimilarity matrix, that should just be blank. What you'd do is you'd take this larger value of these two. So you'd now say the difference between x2, x3, and x4 is whatever the maximum difference was originally between those. So it wouldn't be 0.2 because it's complete linkage. We'd take the 0.45. So we put 0.45 there. 0.4 is the next smallest one. So we merge x2 and x3 with the x5 cluster, and that gets us this cluster of 3 things. I'm just going to turn off all the sounds because I'm getting a lot of... Did I? Okay, cool. Yeah, so I merge these into a cluster at height 0.4. Then I have this dissimilarity matrix. 0.7 is the next smallest, so I merge x1 with x4 at height 0.7. And then finally, we're left with 0.9, and we merge the remaining 2 clusters at a height of 0.9 into this mega cluster, where everything is just... That's not an official term, but everything is just in one cluster. And we should get a dendrogram that looks something like this. Regarding this whole crossover thing, this was before I discovered the ambiguity trick. So what I would actually do now is do the lowest height one first, then the 0.4, then 0.7, then 0.9. I don't reckon we'd get marked down for doing something like this, but just this crossover leads to some ambiguity as to how these two are sort of merged. So that's why I'd try to avoid that. Yeah. Okay. Part B. Is the line in the top mandated? What do you mean? Is it needed? Like, I don't know if this is needed or not. But I guess if we're trying to create one cluster, it's just for, like, completeness sake. We can then just do this. But I don't know whether it's needed or not. Most diagrams I've seen of dendrograms, though, do include that sort of top line. Yeah. Okay. Is it needed? Yeah, I'm not sure. Part B was... Assume that a clustering algorithm produces the following 2 clusters. C1 equals x1, x2, and C2 equals x3, x4, x5. For each of the observations in cluster C1, compute the silhouette coefficient using the information from the dissimilarity matrix, comment on the suitability of their assignment to cluster 1. This wasn't too bad. All we had to do is get the values and just sub it into here. So I can show you guys what calculation I did. Does anyone want to share their solution to this? Put a little stump. Yeah, that works as well, Ollie. And yeah, that's the order I probably would have done it in. Okay, Phoebe sent a solution. Let's paste this. Okay, cool. Yeah, this looks quite similar to what I got. So we have our cluster 1 is of these two vectors. And then we're saying A and B of x1 and is the average distance of x is okay. So we've worked out the silhouette coefficient for this point here, and then the silhouette coefficient for this point here. So for this first point, yeah, Danny's also said in chat, we get a silhouette coefficient of 0.5714, and we just do that by subbing in the values into this formula. So we work out the A value, the B value. A is the average dissimilarity. So yeah, we've got this equation here where it's the sum of all of the distances from X in that cluster over the total number of values in the cluster take away 1. This is correct. I'm just trying to figure out why we did take away 1 here. Some of all the... Oh, right, because we don't want to include that point itself. Yeah. Okay, so this is the average distance to every point in that cluster. And then we have Bx, which is the minimum average dissimilarity of X with respect to all the clusters which it does not belong. So we look at all of the distances in cluster CK, which is some other cluster. So in this case, this is our cluster 2 with 3, 4, 5. And we work out the average of those distances. And then we just sub it into this formula and we get 0.5714. For x2, if we do the same thing here, we get minus 0.0222. Yeah, that looks more exact than what I got. I got minus 0.233, but I think you've not rounded, so that would be a more correct answer, I'd say. Awesome. I'll paste in what I did as well. This is how I approached it. So again, yeah, SC, I worked out the A value for both of the points, the B values for both of the points, and then I just worked out the two silhouette coefficients by subbing it in. And obviously a higher silhouette coefficient means that a point is well suited to the cluster it's in, whereas a negative silhouette coefficient would mean that it's more optimally clustered in a different cluster. So that's kind of what it tells us. I think you put an extra 0. Where, Ash? Oh, yeah. I don't think this 0 should be there. But otherwise, everything's correct. Yeah. But nice. Okay. Let's move on to question 2. Supervised learning. Okay. Okay, the following pseudocode represents one iteration through the training set for gradient descent applied to univariate linear regression. We set our cost W0 and W1, and then we run this for loop. Assume that the value of the learning rate alpha is 1. Give the numerical values of cost W0 and W1 at the end of the execution of this pseudocode for the following training set. Show all your working. Okay. I did this without and realized. Depends. Yeah. I don't think they'd confiscate the 991EXs, but based on Matt's response, I highly doubt they will. I don't think the invigilators will care enough, to be honest, because it's been permitted, so. Okay. This is what I did for 2A. So let's make that a bit smaller. So initially our cost, our W0 and our W1 is 0. I'll paste the pseudocode on the right as well. Okay, so initially our cost W0 and W1 are 0. And then this is our first loop through the for loop. So this is our point, our first point in the training set. So I've said f equals 0, cost equals 1. W0 is -1, W1 is 3. Just based on these calculations. And that gets us our new cost W0 and W1. And then I looked at the second point in the training set, updated the values accordingly, got our next cost W0 and W1. And then we looked at the next point in our training set, calculated the values accordingly, and got our final cost as 11, W0 as 1, and W1 as 8. Did anyone get anything different for this? Or did we all get this? 11, 1, and 8 for cost W0 and W1. 10 minus 2, 0 for number 2. 10 minus 2, 0. Do you want to send your working, James? I mean, we can take a look. It's on paper. Oh. Okay. I mean, you can send a picture if you want. Suppose... Oh, right. That's a different thing. I'm just going to box these all up and label them. 11, 1 minus 4. Oh, okay. Let's take a look at this. So first run we get 0, 0, 0, and then next run we get 0 plus 1. Wait, 0 plus 1 equals 1 for the cost. The cost would be, yeah, 1. Weight 0 is -1, and weight 1 is 3. Cool. Okay, so I got the same as you on that. And then 2 minus 2, 2. Yep. And then 3. So the cost is 2 plus 5 minus 2 squared, which is 11. Yep. Minus 2 minus 2 minus 5 is 1. And 2 minus 5 times 2 is 2 minus 6. Wait, 2 minus... I think this is where some people messed up. So 2 minus 5 times 2 is 2 minus 3 times 2 is 2 minus 6, which is 8. Yeah, don't worry. But yeah, I think with these questions, they're very simple to like do computationally, but the one thing where I think most people will mess up is the minus signs and making sure that you're doing that properly. So like triple check your answers, guys, when it comes to that. Yeah. But cool. That's question 2. 2A at least. Okay, what's 2B? Suppose that you want to use a k-nearest neighbours classification, but the distance metric is not explicitly specified to you. Instead, you're given a black box where you input a set of points and a new point x, and the black box outputs the nearest neighbour of x. Can you construct a KNN classification algorithm based on this black box alone? Does anyone want to describe their solution to this? Do anyone want to explain their solution? Feel free to unmute if you want to talk, or you can just send a fat essay. Nice. I don't think we needed to do pseudocode. I think it just wanted us to explain, right? Can you construct... I mean, it says construct an algorithm, but I guess if we explain it, that could also work. But let me paste in Phoebe's pseudocode solution. Okay, KNN. So we input the training set, some new point X, and what is K supposed to be? Oh, K is just the number of neighbors we look at. Okay, so labels equals an empty an empty list. If K is more than 0, for in I equals 0, I is less than K, I++, labels.append, blackbox.label, training set X. Okay, and then temp set equals training set dot remove, blackbox.closest neighbor, training set X. Okay, that makes sense. One thing, would we want to use the temp set up here, not the training set? So would this be temp set we pass into here? Because that's the one we're removing from. And then up here we'd want to do something like temp set equals training set. Just so that we copy the training set and then we're removing from the temp set and then putting the removed from temp set back into the black box. If not, yeah, no, that's fine. But yeah, that's a good solution. That's kind of what I said, but I just explained it. I didn't write the pseudocode out. And then so we keep removing from that set of neighbors until we have however many neighbors we need. And then we're appending all of these neighbors to labels. And then, yeah, and then we just find the most populous label, which we do in a normal KNN sort of thing. Awesome. Yeah, that's basically what I did. Let me paste my solution as well. Okay, so yeah, we initialize it with a K value. Value determines the number of neighbors to check. So with a set of points and a new point X, we can pass them all into the black box to get the closest point to X. And then we can remove that point from the set we passed in, just so that we pass in all but that point. And we keep doing this until we have enough neighbors. And then with all the neighbors we've basically popped or we've got from that black box, we can then just do a majority vote with whatever's in there. Cool. Does that sort of make sense to everyone, how we've done that? Yeah. Awesome. It does. I think it's because we've been accustomed to A-levels, Millie, that it just feels like not enough. But all the marks are really inflated. Yeah. Okay. 3. Let's get to 3. Optimisation. Oh, speaking of inflated marks, give 1 strength and 1 weakness of hill climbing. Justify your answer. 10 marks. Right. Okay. Can anyone give me a strength or weakness? And justify it. No heuristics needed. Yeah. Oh, I need to type. No heuristics needed. Get stuck in local minimum / maximum. Yeah. Hill climbing is not complete. Yeah, good. So if it finds an asymptote, it will go on forever. Can get caught in infinite loopy paths? Yeah, I think that's quite similar to this. Can get stuck in infinite / loopy paths. Advantage, greedy algorithm. Less computing power / easier to code. Cool. That's a good point, Tony. But it could also, I feel like it could be the opposite. I think, I don't know how to frame that as an advantage. Okay, let's see what Android put. 1 strength of hill climbing is that we can move to a more accurate data point closer to the goal, as it's a greedy search, meaning it will select the next closest point without searching further. 1 weakness is that it can get stuck in local maximums and plateaus. Oh yeah, plateaus is also can get stuck in local min-max or plateaus. Lower time complexity, I guess, yeah. Lower time complexity since greedy. Compared to something like simulated annealing, I guess. Yeah, because once we reach some local solution, we just terminate. Cool. I think it should be a separate point. Easier to implement in code. Only looks at immediate neighbors. Yeah, that's a weakness. Cool. Okay, I think that's enough positives and negatives. But do they all make sense? Are there any on here that don't make sense to anyone? One leak code. Wasn't sure if this is that good or bad. Yeah, if it isn't deterministic, I mean, why is it good for things to be deterministic? It's good. We can always reproduce it. I guess. Yeah, making it look like 10 marks. This is what I put. I think this would hopefully constitute 10 marks. I'll send my solution. I'll put it on here. But again, yeah, I feel like it doesn't deserve 10 marks. I feel like we all have that kind of A-level imposter syndrome. But low space complexity... Yeah, that's actually a good point. Low space complexity. And I think to get the 10 marks, you just want to expand on that. Yeah, explain it, as Phoebe said. So like low space complexity, because we're only storing local variables. We don't keep or retain any information, because hill climbing is a local search algorithm. We're only storing the current state and computing neighbor states. Yeah. Okay. Yeah, this is what I put. One strength is that it isn't computationally heavy. One weakness is that most of the time it will not reach an optimal solution. It's probably the thing that's going to make us lose marks. Yeah, it's tricky to sort of say what's going to catch us up. We'll see. Okay, let's look at part B for the optimization section there. Okay, how am I going to get this on here? I want to fit this all onto one page, ideally. But it's a long question. Okay, it fit on one page, but... Okay, so let's just read through it together. Optimization problem. A builder has n possible clients. Each client would like the builder to undertake a job that takes hi hours to complete. The builder wishes to decide which clients to accept over the next 30 days so as to maximize their income while ensuring that they do not work more than 7.5 hours a day. This problem can be mathematically formulated as follows. Maximize f of x subject to g of x equals 1 over 30 times the sum of xi times hi for all values of I up to n. Take away 7.5 is less than or equal to 0. That's a bit of a mouthful. I'll let you guys have a read of that. And then x is a vector of size n of just 1s and 0s on whether or not the builder is taking that job or not. Yeah. So one way we could do this is with simulated annealing. Representation. So this is the algorithm design. Representation. A direct representation of the design variable x. A vector x of size n, where for all I in 1 up to n, xi is 0 if the builder does not accept the job, and 1 if they do accept the job. Initialization procedure. So this is how we create our initial candidate solution. And it looks like what we're doing is we're just randomly assigning values. So randomly choosing which jobs to take and which jobs not to take. That's how we decide what our initial solution is. In terms of our neighborhood operator, to generate our neighbors, we're saying current solution x, number of possible clients n, and we want to output a neighbor given a current solution. So we copy x, we pick a random index in x, and we flip it. So if it's 1, which means we're doing the job, now we don't do the job. If we aren't doing the job, then we are doing the job. That's what this 1 minus xi does. And then if g of x is greater than 0, so g is that constraint. So checking that we have the right amount of hours. If it's greater than 0, then that means our constraint is invalid. So we set xi back to 0. And then we just return that. So we want to flip a random value in our solution until it's sort of valid in that constraint. Danny, sure, yeah. Are you happy to explain the constraint? So, yeah.
Well, yeah.
Sure, go for it.
So can you scroll back up to g of x,
Yeah.
please? Yeah, because I was thinking, you're basically, because it's less than or equal to 0, you can rearrange it to be less than or equal to 30 times 7.5. So it's basically checking that for the whole month, he's worked less than. So let's just say hypothetically he worked 7.5 hours every day for 30 days. You would have worked 30 times 7.5 hours. So all it's checking is that over the entire month, he's worked less than that. So it is checking that the average number of hours per day is less than 7.5. It doesn't actually say that on a given day, he can't work more than 7.5.
Yeah.
So like he could be working 10 hours one day and then 3 hours the next, and it would actually allow that.
Another way of imagining what like Danny's mentioning here is, if my pen starts working, if we rearranged this, we'd get 1 over 30 times n I equals 1, xi hi is less than or equal to 7.5, times both sides by 30, and now we have 30 times 7.5. All we're doing is we're checking the sum of all of the tasks times is less than this. We're not doing any daily checks here. We're just checking the average, essentially. Yeah. Like, no, so the question asks us if. Oh, wait. Yeah, you're right. The question did not ask us to check the constraint. But, I mean, it says, are the representation, initialization, and neighborhood operators valid? Wouldn't this be part of the representation? Wait. Because, yeah, you do not need to check whether the problem formula. Oh, okay. We don't actually need to check that the constraint is invalid. But I also did that off the bat. Yeah, no, okay. So I'll just make this a bit lighter. This is not that relevant, but yeah, it's a good thing to notice though. Yeah. Right. Okay. So the actual question is asking us: are the representation, initialization, and neighborhood operators correctly designed for this problem? Assume that we wish to deal with the constraints of this problem based on the design of the algorithm's operators. Justify your answer by explaining why all 3 operators are suitable or what is wrong. Okay, so we assume that the problem formulation is correct. You do not need to consider how efficient the design is, just whether it works or not. And it's acceptable for the neighborhood operator to sometimes generate a neighbor that is the same as the current solution. I know some people posted some answers earlier. Okay. Let me paste this in. Okay, this was Phoebe's response. Does the representation reflect the intended problem? Yes, design variable is variable where the builder accepts or rejects the job. So we've got a design variable and it's just storing zeros and ones as to whether or not the builder's taking the job or not. So I believe that's fine. Yeah, Lumi, I think that's what. Wait. Should be a for loop rather than if statement. What do you mean? So here, because right now we're checking if the constraint isn't met, then whatever we just changed, change it back. So this would actually work, right? A list of generated solutions. Right. Yeah, no, I see what you mean. But I think we just need to pick a random solution. Yeah, I think we just need to pick a random solution. And as Rory said, it works. It's just not the best. It's not the most efficient. But the question says we don't need to consider how efficient the design of the operators is, just that it works or not. So, I think this would still be a valid way, like a valid neighborhood operator. So the initialization reflects the intended problem because it's somewhat random. It just decides whether a builder accepts or rejects their jobs. And then in terms of the neighborhood operator, it's also valid. It also like works because if the constraint is broken, then we just flip that back to a 0 so that it's however it was before. Are we setting it to 0 or 1? Okay, cool. Yeah, I'm setting it to 0. Okay, let me just... This is something I was wondering about as well, what Ash has sent. So, in the actual pseudocode for simulated annealing, we generate neighbor solutions and then pick one. But I'm just thinking, do we generate all the neighbors and then pick a random one? Or can we not just generate a random neighbor and pick that? Because I feel like it will do the exact same thing, and we're just adding unnecessary computations by generating every possible neighbor. If we can only generate neighbors sequentially, I'd understand why we need to do that, because then we can only pick a random one from the ones we've chosen. But if we're generating it by random, and simulated annealing works for any neighbor, and we're going to just pick a random neighbor anyway, surely this can just work. Actually, why can't you generate every possible solution and pick one closest to 7.5? That would be something like hill climbing, Lumi. So that's where we pick a neighbor that improves the solution all the time. Doesn't the initialization also need to ensure a valid random solution is generated? I don't think so, just because we'd embed our constraint into the function, and then when we're actually checking that neighbor, then it will just count as something that's worsening the solution, but it would still be something it would still be a candidate solution. Let's say we have a neighbor operator that will generate... Okay, let me paste this as well. Let's say we have a neighborhood operator that will generate feasible solutions for the current solution. Would we need to generate a list or nah? For simulated annealing, if you generate a list but only keep the best of them and discard the others. Oh. Okay. If solutions are generated always according to a pre-specified condition, then you need to generate them and pick one at random. Right, so... Okay, so because we're not generating them sequentially, we're just generating a random one with this neighborhood operator. If this was something like flip the first bit, or like flip the first value, and then flip the second value, and then flip the third value, then we'd have to generate all of them and pick one at random. But because this is actually just using randomness in the actual operator itself, we can just use the neighborhood operator and then just use that as the neighbor we consider as the next one to move to. That's what I've got from that. Yeah. Does the initial... I don't believe it has to be feasible. Well, yeah, no, the initial solution doesn't have to be feasible, because with a lot of the problems we went through, even in lectures, the initial solution wasn't necessarily feasible, but then due to how we then decide to move to neighbor solutions, we'll find a feasible solution. Yeah, the neighborhood biases us towards a feasible solution. Did you go through simulation annealing on tape? I can go through it after, Phoebe, don't worry. Gonna take 8. Yeah, but eventually we'll find something, Ash. Eventually we'll find a feasible solution. Would you get marks for explaining why this is the case? Possibly. You could just say the neighborhood. I mean, what you'd say about the neighborhood operator to build on that is saying that this if statement ensures that we don't go from a feasible solution to an infeasible. I mean, this operator doesn't guarantee that we go from an infeasible to a feasible. We might go from an infeasible to an infeasible, but we'll never go from a feasible to an infeasible, because as soon as we swap something and it breaks the constraint, we'll instantly just swap it back. It just means merely after enough iterations, eventually we're more likely to get to a feasible solution because of this. So if we start at an infeasible solution, we can either go to an infeasible or feasible solution. And this is like a dead end. From feasible, we can't go back to an infeasible solution. So we'll always, as soon as we get to at least one feasible solution, we're going to stay there. From feasible, we can only get to another feasible solution. And so on. I'm not sure if it's a definition, Danny. I think it is possible to have a neighborhood operator that doesn't always tend to feasible solutions, but that depends on your search space, and that depends on how you've defined the operator. So the neighborhood operator is just... I don't think so, Ash. The cost would be less than the current solution. Less than or equal to. So yeah, the sign would be the other way around. I'm recording it, Tony, don't worry. But that kind of makes sense. Yeah, quality, yeah. But does that kind of make sense to people? I need to label all of these imported answers. Okay, that's good. Are there any questions about the paper? I think that was the last question. Question 4. Question 4. Question 4. Question 4. Question 4. Did I miss a question? Is this only question 3? Oh, this is question 3. Okay, question 4. Right. Search. Let's go. Consider a problem with two possible actions, A and B. The cost of A is 2 and the cost of B is 1. The shallowest goal node can be found at any level of the tree, and the problem solution may involve a sequence of these actions. Is BFS optimal to solve this problem, given the cost function? Justify your answer. How have we decided to answer this, guys? Not optimal as cost can change. No, because it very short path. Yeah, so both of you are correct. No, it can find a short path in terms of number of actions taken, but will not find one with, will not necessarily find one with the lowest cost. Good. So for example, as Danny said, a solution of A's, so say we start at this initial node and we do an A, say this is a goal node, but then we do something like B, and this is a goal node. This goal node will have a cost of 4, because we're going to do B 2 times, whereas this goal node is going to have a cost of 3 because we're doing A 3 times. So BFS would count this as our shallowest goal node and it would go with this, whereas we want to go with this lower cost solution, which is only a cost of 3. Yeah. So BFS is not necessarily optimal. I'm just trying to think how we can stretch that into a 10-mark answer. This is how I answered it. A BFS search explores the nodes in a graph on a level-by-level basis. Since the cost of expanding and adding an A is double that. A is... Yeah. Oh, okay, I did this the wrong way around. Imagine these are B's and these are A's. Since the cost of expanding an A is double that expanding a B, BFS may not be as efficient or optimal as iteratively expanding from the node with the smallest path cost that we haven't expanded yet. For example, instead of expanding A, B, AA, AB, BA, BB, so this is our sort of BFS list of nodes we'd visit. Instead, we can expand this. So we can do BA, then we can expand BB, which is a cost of 2, then AB, which is a cost of 3, and we can do it in ascending cost instead of doing it like this. We're looking for the shallowest goal node. I mean, what we kind of want to do here is we're assuming we want to minimize the cost function because they've given us a cost function. And so in order to minimize the cost function, this node here isn't shallower than this node, but it's a lower cost. So this is what we'd want to go towards, and we wouldn't want to go towards here. Yeah, exactly. So that's why I said something like a distance space, like A star search or Dijkstra, would be more optimal. Because then we can find the shallowest goal node faster as well. That's probably not the best way to do it. Shallowest goal node with lower cost. Yeah. Okay, let's look at part B. Okay, an agent must traverse a maze. Could you write that to expand your answer then, like suggest A star? I guess you could. Use a path finding algo like A star. I guess that could possibly get you. How I justify it, Lumi, is something like this. So saying with BFS, we'd expand it in this order. So like A, then B, then AA, then AB, then BA. Whereas with A star, we're looking at the lowest cost solutions first. Here we're looking at a 2 cost, a 1 cost, a 4 cost, a 3 cost. Here we're doing it in like ascending order. So we're looking at the lower cost solutions before we then look at the higher cost solutions. Yeah. Because with A star we actually use an evaluation function to decide which node to expand. So we can expand the ones that are shorter in terms of the cost first. Yeah. I don't know if that makes sense. Dijkstra's would also work, yeah, because we're not really told about any heuristic here, so Dijkstra would be the exact same, yeah. Is that state as well? Yeah, it is a bit of an ambiguous question, but I feel like a lot of our questions are going to be kind of ambiguous like this. So yeah, not too sure. Yeah. I think if you can say something that makes sense and justify it, even if it's not exactly what they're looking for, if you've given some sort of viable response as to why BFS is optimal or not optimal, and you justify it, I feel like you'd get the marks. Wait, am I tripping? What are you tripping about, Ash? This isn't 2023, is it? This is the 2023 summer paper. I think the cost of A or B makes A star not feasible as a solution. Why not, Lumi? You don't need to... Yeah, we don't... Yeah, exactly. We don't actually... We can just do A star without a heuristic. So it would essentially just be Dijkstra. Yeah, Dijkstra would make more sense than A star here. Yeah. A star without the heuristic is just Dijkstra. Yeah. Yeah, exactly, Danny. We just expand the one with the shortest cost to it, because that's how Dijkstra works. Isn't this the same as earlier as well, though? Like... Bro, this isn't 2023. This is the paper it is. Main summer exams 2023. BFS doesn't work because they have different action costs. Yeah. BFS just considers how many actions we've taken, not the actual cost of the action. So to introduce some sort of consideration of that cost function, we'd need A star or Dijkstra. Okay. Let's move on to part B. An agent must traverse a maze in order to find and collect a treasure. This task can be formulated as a search problem, as in the following. So we have an initial state where we start at A1. The agent is in E5 is our goal state. Actions. Move n prime. Moves the agent from state n to n prime. That is to the left of, right of, above or below state n. Transition model. States depicted in black are considered obstacles and cannot be traversed by the agent. Path cost. Each action has cost 1. Generate the A star tree until the goal node is found. And this is the heuristic they want us to use, which is just the...
Manhattan distance.
Yep. I'm confused why this 3's here. Pi minus Qi. This is Manhattan from n to in goal. I equals 1 up to 3. So P1 take away Q1 plus P2 take away Q2 plus P3 take away Q3. But there's not 3 components in the position.
Yeah, I can't lie. I thought they made a mistake there. I literally just took it at face value, just used the Manhattan distance because they've just said what Manhattan is. I think they might have made a little mistake in writing the formula for Manhattan.
Yeah. Yeah, I think it should be 2 then, yeah. Okay, so, how did we do this, guys? Does anyone want to talk us through it? Okay, I'll talk through my solution, and if anyone finds anything wrong with it, let me know. So I started at A1. From A1, the only place we can get to is B1, so down here. We can only move down. Okay, so G is our total path cost to that point. H is our heuristic to that point. So we get to B1. From B1, you can only get to B2. Let me actually paste this down here as well. B2, I recalculated the heuristic to be 6. Pretty much all of the things here are 8. So f of n, or f of any node is pretty much 8. From what I've done. So B2, we expand either C2 or B3. C2, we go to D2. Then B3, we go to B4. D2, we go to E2. B4 we go to C4. So it's basically expanding these, and then from E2 we can either go to E3. From D4 we can go down to E4. Why have I crossed that out though? I'm not entirely sure why I've crossed that out. You never actually visit A4 actually though, right? Yeah, we never actually go up here just because it's Yeah, because the cost would end up being 1, 2, 3, 4, 5 plus 1, 2, 3, 4, 5. The cost would end up being 10. F of n would be 10, and so we don't explore that because the 8 is better. Yeah. And then from E4 we explore E5, and then we're at our solution. And so this is the sequence of nodes. This is the order in which we visit those nodes. Our solution is the sequence of actions we take to get down to E5. So I just wrote it as this move function, like move from A1 to B1, B1 to B2, B2 to C2. Are we sure we have A4 in the frontier? Because I feel like so from B4, so you just drew A4 here. Okay.
Because if you expand a node, you need to expand all of its successors, not just one of them.
I
Like
guess,
you need
yeah,
to
because
you need to generate all of the neighbors. You can't generate just the one you want, even if you just expand. You do
yeah, so
expand like
then
all or none.
f of A4 would be 5 plus 5, which is 10. And so then that's why we wouldn't then expand that. Okay, so did you, for C4, did you also have a branch here going to C5? Did you
Yeah,
write
yeah,
that in your
I
frontier?
did.
Okay.
Yes.
C5 would be 1, 2, 3, 4 plus.
And then C2 as well, I think, somewhere.
Yeah, 1, 2, 3, 4, 5, 6 equals 10. C2 would be C2.
C2's in my frontier at the end, I don't know.
I've got it here.
Did you go down that route in the end?
Yeah. Because eventually you have these two in the frontier. You have C4 and you have C2. And you want to do the one that's alphabetically like less. So C2 is the one you'd then go down, not C4.
Oh, because
you do this
is that
one,
what it
then
said?
you
If
do
they're the
this.
same, if they're the same cost, you go with the alphabetically one.
Yeah, so expand the nodes in alphanumerical order.
Okay. Right. So you do actually have to expand C2 just for
Yeah.
that. Okay.
D2.
But then
So
you'd
you
go
just
back to being C4, right?
yeah, but then as soon as you do that to D4, then you'd carry on this D2 before the D4, and then go down to E2.
Okay.
F of D1 equals 1, 2,
Maximal
3, 4,
inefficiency.
5 plus 1, 2, 3, 4, 5 equals 10. Shay, it's B3 expanded first. Yeah, you'd expand that first, and then you'd expand. Yeah, you'd expand this first, then you'd expand this.
C4.
Then you can't expand that. You'd expand. This is the order I expanded it in, basically.
After B4, you'd expand C2, yeah?
After B4, I expanded C4.
I thought you said it has to be like the one with the lower letter and stuff.
Yeah, and B4 is less than.
Oh, after B.
C2.
Oh, yeah, okay, right.
Yeah. Right?
Wait.
Sequence of visited nodes, solution, and then cost is 8 because we took 8 actions. This is the tree I got. Let me know if anyone's got any disputes against it.
Why is C2 visited before B3?
Why is C2
Yeah, that's what I was
B3?
going to ask.
Let me see. Okay, so initially we're here. B2, we expand into these two. Why have I done that? Yeah, I would do the B3 first actually. So these two should be swapped around. So I do the B3, then I do the C2. Just because B2 is less than B3. And then now I have these two in the frontier. Then I do the B3 to expand to B4, visit B4. Then B4, I'd visit C4. Yeah, so B4, C4. And then I have C2 and I have C4 in the front here. Then I do D2, then D4, then E2, then E3, then E4, then... Oh, right, no. Then E4 from... Ooh. C2, B... Yeah, so C2 would go here, then B4. But I think... Because, yeah, so we do B3, then C2, then B4, James. Wait, I've lost track of what I was doing. So B4, yep. C4, yep. D2, then D4, then E2, then I reckon we'd do this E4 here, and then we'd do E3, and then we'd do E4, and then we'd do E5. Once you get the right side as... Yeah, so this would go to E5, right? Not this side. Yeah, okay, that's what I'm thinking. So E5 is supposed to be off this chain here. And this E4 wouldn't be expanded because this one would be here. So that would be a loopy path. It just says f of n is our evaluation function, Lumi, and then f of n equals g of n plus h of n. So in all of these cases, it's pretty much 8. So we just... Our evaluation function is just 8. We don't prioritize anything. Yeah, so the tie is... When we have that tie, it's just whichever one comes alphabetically first. Or alphanumerically first. In this case, D4 is before E3. So that's the one we'd expand. D4 to E4, yeah. And then between E3 and E4, we wouldn't expand we'd expand E3, but we can't expand to E4 because E4 is loopy. That already exists in our frontier. So we wouldn't expand anything from E3. And then we'd just expand E5 from E4 to get to our goal state. So our actual solution would be move from B2 to B3, and then move from B3 to B4, and then move from B4 to C4, and then move from C4 to D4, and then move from D4 to E4, and then move from E4 to E5. The cost would be more than 8 in this case though, right, Danny? Surely? Because this would be 1, 2, 3, 4, 5, 6, 7, 8, 10, 11 then. I think. I mean, I'll send this PDF out. If anyone does have any light bulb moments about anything here, just drop it in the AI chat. But yeah. 8 because you travel down 8 edges from A1 to E5. 1, 3, 4, 5, 6, 7, 8. Oh, right. Oh, what have I done? B1 to B2, B2 to B3, B3 to B4. Oh, I've just... Okay, these 3 shouldn't be here. So yeah, it would be 8. I don't know why I didn't correct the right ones. So this would be 8, yeah. Yeah. No, you're right, Danny. Okay, wait, someone's asked a question about question 3. What if you initialized it at 1, 1, 1, 1, 1, 1, 1, 1? Okay. If we did that, then obviously that would be a candidate solution based on a design variable. There's no constraints for that. So then when we find a neighbor, we'd end up swapping them to zeros one at a time. So first we might swap this one to a 0, then we might swap this one to a 0, And we'll keep doing this until the weight is valid. And as soon as the weight is valid, then we'll start swapping random ones to 1 and swapping random ones to 0. So we'd slowly make our way to it being valid on that constraint. If it's invalid, then you just return. No, so it doesn't quite flip it back. So it picks a random index, so it will swap one of the 1s to a 0, and then if it's greater than 0, if the constraint still isn't met, it will just overwrite that 0 with a 0, so it won't make a difference. It will just change one of those 1s to a 0, essentially. Yeah. Cool. Are there any questions about same but in the reverse? Oh, right, yeah. If there's no questions about the paper, I'll stop the recording, and then whatever topics people wanted to just talk over, we can do after. Oh, 4B. Yeah, 4B, what about it? Oh, okay. 1B. Danny, what's up with 1B? What does it mean for the... Okay, so if it's positive, that's good. That means the point is well suited for that cluster. If it's negative, that means the point is better suited in a different cluster. So, for example, if we had these two clusters, we'd expect the silhouette coefficient of this red point to be negative. And we'd expect the silhouette coefficient of, say, this red point to be positive. The closer to 1, yeah, the better it's suited. And the closer to negative 1, the worse it's suited. If it's negative 1, then it's just in the wrong cluster. For 4B, I think would also need to consider move back action, for example, at B1 you should also consider. For 4B. I mean, it says don't consider loopy paths, right? If Given also... Wait, I see what you mean, actually. But I guess... I feel like that would be a bit overkill. Like, I don't think they'd expect us to fit all of that on the page. Because then we'd have to have states coming off. So then B1 would then have an A1. This would have a B1. I don't know how... Does he consider them? Oh, right. Okay, then we might have to. If it's not explicitly stated. So this would go to A1. This would go to B1. Okay, I'll do it in the shade of grey. But yeah, so that goes to A1. That goes to B1. That goes to B2. That would go to B2. That would go to C2. This would go to B3. This would go to B4. I don't know, because it says keep the node that has been added last into the frontier. I don't expect that we would want to put loopy states. Because if it's an A* search, if we think about how we do an A* search, it's not like a BFS or anything. We actually, as part of this A* search algorithm, we just keep the path with the shortest distance. And then we don't overwrite that distance, so we don't store that second distance. Yeah, I don't think we'd have to loop. For this solution, you need to... Thank you for sharing your solution. Such the algorithm would keep A1, but since the cost of it will never be visited / expanded. Okay. Yeah, I feel like it doesn't really make sense to do that with the context of doing an A* search. I see what message you sent though, so I guess that's kind of conflicting. no, that's fair. I mean, you could do it in case if you have some time left over, but yeah, I don't know. Maybe I'll send a message on the Teams or something and see what they say. Or if someone else wants to. I'll send the PDF in the chat as well. So if there's anything you're unsure about, feel free to go over it. All good. Thanks for dropping by. If there's any... let me stop the recording actually. This PDF will be posted in the Discord. Yeah.